Hello, welcome back. Let's reading some more. My apartment very hot, like 30 degrees. But I need to close my door. So I finish eating. It's not 3 p.m. soon. So I like to read this, then make a video in my language, Danish, about it. I was supposed to do in English too, but I don't have the energy. So I have a low number of subscribers. Nobody is watching this. But it's not why I do it. I do it because I like to read it. I like to read about it myself.
Lockheed SR-71 Blackbird. SR-71 redirects here. For other uses, see SR-71, disambiguation. The Lockheed SR-71 Blackbird is a retired long-range, high-altitude, Mach 3 plus strategic reconnaissance aircraft developed and manufactured by the American aerospace company Lockheed Corporation. The SR-71 has several nicknames, including Blackbird and Habu. The SR-71 was developed as a black project from the Lockheed A-12 reconnaissance aircraft during the 1960s by Lockheed's Skunk Works division. American aerospace engineer Clarence Kelly Johnson was responsible for many of the aircraft's innovative concepts. The shape of the SR-71 was based on that of the Lockheed A-12, which was one of the first aircraft to be designed with a reduced radar cross-section in mind. Initially, a bomber variant of the A-12 was requested by Curtis LeMay, before the program was focused solely on reconnaissance. The SR-71 was longer and heavier than the A-12, allowing it to hold more fuel as well as a two-seat cockpit. The SR-71's existence was revealed to the public in July 1964. It entered service in the United States Air Force, USAF, in January 1966. In 1989, the USAF retired the SR-71, largely for political reasons. Several were briefly reactivated during the 1990s before their second retirement in 1998. NASA was the final operator of the Blackbird, using it as a research platform. It was retired again in 1999. Mission equipment for the plane's aerial reconnaissance role included signals intelligence sensors, side-looking airborne radar, and a camera. During missions, the SR-71 operated at high speeds and altitudes, Mach 3.2 and 85,000 feet, 26,000 m, allowing it to outrace or entirely avoid threats. If a surface-to-air missile launch was detected, the standard evasive action was simply to accelerate and outpace the missile. On average, each SR-71 could fly once per week due to the extended turnaround required after mission recovery. A total of 32 aircraft were built, 12 were lost in accidents with none lost to enemy action. Since its retirement, the SR-71's role has been taken up by a combination of reconnaissance satellites and unmanned aerial vehicles, UAVs. A proposed UAV successor, the SR-72, is under development by Lockheed Martin, and scheduled to fly in 2025. As of 2024, the SR-71 holds the world record, which it set in 1976, as the fastest air-breathing manned aircraft, previously held by the closely related Lockheed YF-12. Development, edit. Background, edit. Main article, Lockheed A-12. Lockheed's previous reconnaissance aircraft was the relatively slow U-2, designed for the Central Intelligence Agency, CIA. In late 1957, the CIA approached the defense contractor Lockheed to build an undetectable spy plane. The project, named Archangel, was led by Kelly Johnson, head of Lockheed's Skunk Works unit in Burbank, California. The work on Project Archangel began in the second quarter of 1958, with aim of flying higher and faster than the U-2. Of 11 successive designs drafted in a span of 10 months, A-10 was the front-runner. Despite this, however, its shape made it vulnerable to radar detection. After a meeting with the CIA in March 1959, the design was modified to have a 90% reduction in radar cross-section. The CIA approved a US $96 million, $758 million in 2023, contract for Skunk Works to build a dozen spy planes, named A-12, on the 11th of February 1960. The 1960 downing of Francis Gary Powers's U-2 underscored that aircraft's vulnerability and the need for faster reconnaissance aircraft such as the A-12. The A-12 first flew at Groom Lake, Area 51, Nevada, on the 25th of April, 1962. 13 were built, 2 variants were also developed, including 3 of the YF-12 interceptor prototype, and 2 of the M-21 drone carrier. The aircraft was meant to be powered by the Pratt & Whitney J-58 engine, but development ran over schedule, and it was initially equipped with the less powerful Pratt & Whitney J-75. The J-58s were retrofitted as they became available, and became the standard engine for all subsequent aircraft in the series, A-12, YF-12, M-21, as well as the SR-71. The A-12 flew missions over Vietnam and North Korea before its retirement in 1968. The program's cancellation was announced on the 28th of December, 1966, due both to budget concerns and because of the forthcoming SR-71, a derivative of the A-12. Designation as SR-71, edit. The SR-71 designation is a continuation of the pre-1962 bomber series. The last aircraft built using the series was the XB-70 Valkyrie. However, a bomber variant of the Blackbird was briefly given the B-71 designator, which was retained when the type was changed to SR-71. During the later stages of its testing, the B-70 was proposed for a reconnaissance forward/strike role, with an RS-70 designation. When the A-12's performance potential was clearly found to be much greater, the USAF ordered a variant of the A-12 in December 1962, which was originally named R-12 by Lockheed. This USAF version was longer and heavier than the original A-12 because it had a longer fuselage to hold more fuel. The R-12 also had a larger 2-seat cockpit, and reshaped fuselage chines. Reconnaissance equipment included signals intelligence sensors, a side-looking airborne radar, and a photo camera. The CIA's A-12 was a better photo reconnaissance platform than the USAF's R-12, since the A-12 flew somewhat higher and faster, and with only one pilot, it had room to carry a superior camera and more instruments. The A-12 flew covert missions while the SR-71 flew overt missions. The latter had USAF markings and pilots carried Geneva Convention's identification cards. During the 1964 campaign, Republican presidential nominee Barry Goldwater repeatedly criticized President Lyndon B. Johnson and his administration for falling behind the Soviet Union in developing new weapons. Johnson decided to counter this criticism by revealing the existence of the YF-12, a USAF interceptor, which also served as cover for the still-secret A-12 and the USAF reconnaissance model since July 1964. USAF Chief of Staff General Curtis LeMay preferred the SR, Strategic Reconnaissance, designation and wanted the RS-71 to be named SR-71. Before the July speech, LeMay lobbied to modify Johnson's speech to read SR-71 instead of RS-71. The media transcript given to the press at the time still had the earlier RS-71 designation in places, creating the story that the president had misread the aircraft's designation. To conceal the A-12's existence, Johnson referred only to the A-11, while revealing the existence of a high-speed, high-altitude reconnaissance aircraft. In 1968, Secretary of Defense Robert McNamara cancelled the F-12 interceptor program. The specialized tooling used to manufacture both the YF-12 and the SR-71 was also ordered destroyed. Production of the SR-71 totaled 32 aircraft with 29 SR-71s, 2 SR-71Bs, and the single SR-71C. Design, Edit. Overview, Edit. The SR-71 was designed for flight at over Mach 3 with a flight crew of 2 in tandem cockpits, with the pilot in the forward cockpit and the reconnaissance systems officer operating the surveillance systems and equipment from the rear cockpit, and directing navigation on the mission flight path. The SR-71 was designed to minimize its radar cross-section, an early attempt at stealth design. Finished aircraft were painted a dark blue, almost black, to increase the emission of internal heat and to act as camouflage against the night sky. The dark color led to the aircraft's nickname Blackbird. While the SR-71 carried radar countermeasures to evade interception efforts, its greatest protection was its combination of high altitude and very high speed, which made it almost invulnerable. Along with its low radar cross-section, these qualities gave a very short time for an enemy surface-to-air missile, SAM, site to acquire and track the aircraft on radar. By the time the SAM site could track the SR-71, it was often too late to launch a SAM, and the SR-71 would be out of range before the SAM could catch up to it. If the SAM site could track the SR-71 and fire a SAM in time, the SAM would expend nearly all of the delta V of its boost and sustainer phases just reaching the SR-71's altitude. At this point, out of thrust, it could do little more than follow its ballistic arc. Merely accelerating would typically be enough for an SR-71 to evade a SAM. Changes by the pilots in the SR-71's speed, altitude, and heading were also often enough to spoil any radar lock on the plane by SAM sites or enemy fighters. At sustained speeds of more than Mach 3.2, the plane was faster than the Soviet Union's fastest interceptor, the Mikoyan-Govic MiG-25, which also could not reach the SR-71's altitude. During its service life, no SR-71 was ever shot down. Airframe, canopy, and landing gear, Edit. On most aircraft, the use of titanium was limited by the costs involved. It was generally used only in components exposed to the highest temperatures, such as exhaust fairings and the leading edges of wings. On the SR-71, titanium was used for 85% of the structure, with much of the rest being polymer composite materials. To control costs, Lockheed used a more easily worked titanium alloy which softened at a lower temperature. The challenges posed led Lockheed to develop new fabrication methods, which have since been used in the manufacture of other aircraft. Lockheed found that washing welded titanium requires distilled water, as the chlorine present in tap water is corrosive. Cadmium-plated tools could not be used, as they also caused corrosion. Metallurgical contamination was another problem. At one point, 80% of the delivered titanium for manufacture was rejected on these grounds. The high temperatures generated in flight required special design and operating techniques. Major sections of the skin of the inboard wings were corrugated, not smooth. Aerodynamicists initially opposed the concept, disparagingly referring to the aircraft as a Mach 3 variant of the 1920s era Ford trimotor, which was known for its corrugated aluminum skin. But high heat would have caused a smooth skin to split or curl, whereas the corrugated skin could expand vertically and horizontally and had increased longitudinal strength. Fuselage panels were manufactured to fit only loosely with the aircraft on the ground. Proper alignment was achieved as the airframe heated up, with thermal expansion of several inches. Because of this, and the lack of a fuel sealing system that could handle the airframe's expansion at extreme temperatures, the aircraft leaked JP-7 fuel on the ground prior to takeoff, annoying ground crews. The outer windscreen of the cockpit was made of quartz and was fused ultrasonically to the titanium frame. The temperature of the exterior of the windscreen reached 600 degrees Fahrenheit, 316 degrees Celsius, during a mission. Cooling was carried out by cycling fuel behind the titanium surfaces in the chines. On landing, the canopy temperature was more than 572 degrees Fahrenheit, 300 degrees Celsius. Some SR-71s had red lines painted on the upper surface of the wing to show no step areas, which included the trailing edge and the thin, fragile skin where the inner wing blended into the fuselage. This portion of the skin was only supported by widely spaced structural ribs. The Blackbird's tires, manufactured by B.F. Goodrich, contained aluminum and were inflated with nitrogen. They cost $2,300 each and generally required replacing within 20 missions. The Blackbird landed at more than 170 knots, 200 miles per hour, 310 kilometers per hour, and deployed a drag parachute to reduce landing roll and brake and tire wear. Acquisition of titanium, edit. Titanium was in short supply in the United States, so the Skunk Works team was forced to look elsewhere for the metal. Much of the needed material came from the Soviet Union. Colonel Rich Graham, SR-71 pilot, described the acquisition process. The airplane is 92% titanium inside and out. Back when they were building the airplane, the United States didn't have the ore supplies, and ore called rutile ore. It's a very sandy soil and it's only found in very few parts of the world. The major supplier of the ore was the USSR. Working through third world countries and bogus operations, they were able to get the rutile ore shipped to the United States to build the SR-71. Shape and threat avoidance, edit. The second operational aircraft designed around a stealth aircraft shape and materials, following the Lockheed A-12, the SR-71 had several features designed to reduce its radar signature. The SR-71 had a radar cross-section, RCS, around 110 square feet, 10 m. Drawing on early studies in radar stealth technology, which indicated that a shape with flattened, tapering sides would reflect most energy away from a radar beam's place of origin, engineers added chines and canted the vertical control surfaces inward. Special radar-absorbing materials were incorporated into sawtooth-shaped sections of the aircraft's skin. Cesium-based fuel additives were used to somewhat reduce the visibility of exhaust plumes to radar, although exhaust streams remained quite apparent. Johnson later conceded that Soviet radar technology advanced faster than the stealth technology employed against it. The SR-71 featured chines, a pair of sharp edges leading aft from either side of the nose along the fuselage. These were not a feature on the earlier three design. Frank Rogers, a doctor at the Scientific Engineering Institute, a CIA front organization, discovered that a cross-section of a sphere had a greatly reduced radar reflection, and adapted a cylindrical-shaped fuselage by stretching out the sides of the fuselage. After the advisory panel provisionally selected Convair's fish design over the A3 on the basis of RCS, Lockheed adopted chines for its A4 through A6 designs. Aerodynamicists discovered that the chines generated powerful vortices and created additional lift, leading to unexpected aerodynamic performance improvements. The angle of incidence of the delta wings could be reduced for greater stability and less drag at high speeds, allowing more weight to be carried, such as fuel. Landing speeds were also reduced, as the chines vortices created turbulent flow over the wings at high angles of attack, making it harder to stall. The chines also acted like leading-edge extensions, which increased the agility of fighters such as the F-5, F-16, F-18, MiG-29, and Su-27. The addition of chines also allowed the removal of the planned canard foreplanes. Air inlets, edit. The air inlets allowed the SR-71 to cruise at over Mach 3.2, with the air slowing down to subsonic speed as it entered the engine. Mach 3.2 was the design point for the aircraft, its most efficient speed. However, in practice the SR-71 was sometimes more efficient at even faster speeds, depending on the outside air temperature, as measured by pounds of fuel burned per nautical mile traveled. During one mission, SR-71 pilot Brian Shaw flew faster than usual to avoid multiple interception attempts. Afterward, it was discovered that this had reduced fuel consumption. At the front of each inlet, a pointed, movable inlet cone called a spike was locked in its full forward position on the ground and during subsonic flight. When the aircraft accelerated past Mach 1.6, an internal jack screw moved the spike up to 26 in, 66 centimeters, inwards, directed by an analog air inlet computer that took into account petard static system, pitch, roll, yaw, and angle of attack. Moving the spike tip drew the shock wave riding on it closer to the inlet cowling until it touched just slightly inside the cowling lip. This position reflected the spike shock wave repeatedly between the spike center body and the inlet inner cowl sides, and minimized airflow spillage, which is the cause of spillage drag. The air slowed supersonically with a final plane shock wave at entry to the subsonic diffuser. Downstream of this normal shock, the air became subsonic. It decelerated further in the divergent duct to give the required speed at entry to the compressor. Capture of the plane's shock wave within the inlet is called starting the inlet. Bleed tubes and bypass doors were designed into the inlet and engine nacelles to handle some of this pressure and to position the final shock to allow the inlet to remain started. Schlie air inflow visualization at unstart of axisymmetric inlet at Mach 2. In the early years of operation, the analog computers would not always keep up with rapidly changing flight environmental inputs. If internal pressures became too great and the spike was incorrectly positioned, the shock wave would suddenly blow out the front of the inlet, called an inlet unstart. During unstarts, afterburner extinctions were common. The remaining engine's asymmetrical thrust would cause the aircraft to yaw violently to one side. SAS, autopilot, and manual control inputs would fight the yawing, but often the extreme off angle would reduce airflow in the opposite engine and stimulate sympathetic stalls. This generated a rapid counter-yawing, often coupled with loud banging noises, and a rough ride during which crew's helmets would sometimes strike their cockpit canopies. One response to a single unstart was unstarting both inlets to prevent yawing, then restarting them both. After wind tunnel testing and computer modeling by NASA Dryden Test Center, Lockheed installed an electronic control to detect unstart conditions and perform this reset action without pilot intervention. During troubleshooting of the unstart issue, NASA also discovered the vortices from the nose chines were entering the engine and interfering with engine efficiency. NASA developed a computer to control the engine bypass doors which countered this issue and improved efficiency. Beginning in 1980, the analog inlet control system was replaced by a digital system, Digital Automatic Flight and Inlet Control System, DAFX, which reduced unstart instances. Engines, edit. Main article, Pratt & Whitney J58. The SR-71 was powered by two Pratt & Whitney J58, company designation JT11D20, axial flow turbojet engines. The J58 was a considerable innovation of the era, capable of producing a static thrust of 32,500 lbf, 145 kN. The engine was most efficient around Mach 3.2, the Blackbird's typical cruising speed. At takeoff, the afterburner provided 26% of the thrust. This proportion increased progressively with speed until the afterburner provided all the thrust at about Mach 3. Air was initially compressed, and heated, by the inlet spike and subsequent converging duct between the center body and inlet cowl. The shock waves generated slowed the air to subsonic speeds relative to the engine. The air then entered the engine compressor. Some of this compressor flow, 20% at cruise, was removed after the fourth compressor stage and went straight to the afterburner through 6 bypass tubes. Air passing through the turbojet was compressed further by the remaining 5 compressor stages and then fuel was added in the combustion chamber. After passing through the turbine, the exhaust, together with the compressor bleed air, entered the afterburner. At around Mach 3, the temperature rise from the intake compression, added to the engine compressor temperature rise, reduced the allowable fuel flow because the turbine temperature limit did not change. The rotating machinery produced less power, but still enough to run at 100% RPM, thus keeping the airflow through the intake constant. The rotating machinery had become a drag item and the engine thrust at high speeds came from the afterburner temperature rise. Maximum flight speed was limited by the temperature of the air entering the engine compressor, which was not certified for temperatures above 800 degrees Fahrenheit, 430 degrees Celsius. Originally, the Blackbird's J58 engines were started with the assistance of two big Wildcat V8 internal combustion engines, externally mounted on a vehicle referred to as an AG330 start cart. The start cart was positioned underneath the J58 and the two big engines powered a single, vertical drive shaft connecting to the J58 engine and spinning it to above 3,200 RPM, at which point the turbojet could self-sustain. Once the first J58 engine was started, the cart was repositioned to start the aircraft's other J58 engine. Later start carts used Chevrolet big block V8 engines. Eventually, a quieter, pneumatic start system was developed for use at main operating bases. The V8 start carts remained at diversion landing sites not equipped with the pneumatic system. Fuel, edit. Several exotic fuels were investigated for the Blackbird. Development began on a coal slurry power plant, but Johnson determined that the coal particles damaged important engine components. Research was conducted on a liquid hydrogen power plant, but its low density meant that fuel tanks would be too large. In practice, the Blackbird would burn somewhat conventional JP7, which was difficult to ignite. To start the engines, triethylborane, TEB, which ignites on contact with air, was injected to produce temperatures high enough to ignite the JP7. The TEB produced a characteristic green flame, which could often be seen during engine ignition. On a typical mission, the SR-71 took off with only a partial fuel load to reduce stress on the brakes and tires during takeoff and also ensure it could successfully take off should one engine fail. Within 20 seconds the aircraft traveled 4,500 feet, 1,400 m, reached 240 miles per hour, 390 kilometers per hour, and lifted off. It reached 20,000 feet, 6,100 m, of altitude in less than 2 minutes, and the typical 80,000 feet, 24,000 m, cruising altitude in another 17 minutes.